Hello and welcome. Have you ever actually stopped to think about the invisible signals constantly flowing all around us, just powering our entire audiovisual world? I mean, whether you're setting up a massive stadium sound system or literally just streaming a movie on your couch, absolutely everything hinges on how we manage these signals. So today, we're unpacking the true DNA of AV technology in this explainer. Grasping these concepts is absolutely crucial for designing high-fidelity systems, and it's going to be your secret weapon as we prep for that professional AV certification exam. So let's dive right in. Okay, so here is our roadmap for today. We're going to cover analog versus digital foundations, translating reality into data, calculating bitrate capacity, codecs and data compression, system noise and degradation, and finally, we'll bring it all together with the master exam synthesis. Section 1, Analog versus Digital Foundations. Let's start right at the bedrock of the AV industry by defining exactly how we capture and control real-world phenomena. Think about an analog signal like a classic dimmer switch on your dining room wall. It gives you this infinite, continuous range of positions between completely off and full brightness, right? The signal varies in direct, proportional relation to exactly where you turn that physical knob. A digital signal, though, is a totally different beast. It's rigid. It's like a 3-speed fan controller. It has discrete, fixed states, speed 1, 2, or 3, and absolutely zero values are allowed in between. You're either on a step or you're not. There's no middle ground. Now, when we apply those two mental models to actual data, it gets really interesting. The analog side captures continuous real-world physics. We're talking sound pressure waves literally hitting a microphone diaphragm, or actual light photons hitting a camera sensor. It flows perfectly. But modern AV transitions that physical quantity over to the digital side, and digital relies entirely on discrete mathematical binary digits, ones and zeros, that are captured at very specific, regular, timed intervals. Section 2, Translating Reality into Data. So let's look at how we actually take those flowing, continuous physical realities and translate them into manageable computer data. Digitization isn't magic, even if it seems like it sometimes. It actually requires 3 very distinct phases to successfully rebuild reality inside a computer. First, we have the original analog source. Second, we apply a strict mathematical sampling grid, which is measured in hertz. And third, we output the final digital reconstruction based entirely on the data points gathered by that grid. The really crucial point here is that the sampling grid operates by taking rapid-fire, timed snapshots of the analog wave. Imagine a continuous analog wave passing through, and a grid just constantly intercepting it, grabbing tiny momentary data points along the way. Those distinct little dots are actually all the computer needs to plot the exact points required for the final digital reconstruction. It's basically a connect-the-dots blueprint. But how fast do those snapshots actually need to be? Well, to ensure mathematical accuracy, we rely on the Nyquist-Shannon theorem. And hey, listen up. This is a critical concept for the exam. The theorem strictly states that your sampling rate must always be greater than twice the highest target frequency you're trying to capture. This theorem is literally a law of physics. If you try sampling at exactly 1 times the frequency, you just hit the exact same 0 point over and over again, entirely missing the actual curve. It basically reconstructs as a flat line. But if you sample at 2 times the frequency, it accurately catches both the wave's peaks and its valleys. This is exactly why the industry standard audio CD samples human hearing, which maxes out around 20 kilohertz at a rate of 44.1 kilohertz. It's more than double the target frequency, which guarantees a perfect digital reconstruction. So while the sample rate gives us our timing, bit depth dictates the precision of each specific snapshot. Think of bit depth as this massive exponential staircase. If you only have a 1-bit depth, you just have 2 states, a high voltage and a low voltage. That's it. But as you add bits, the number of available states to describe that exact moment increases exponentially. By the time you get to standard 16-bit audio, you aren't just choosing between 2 states anymore. You have over 65,000 distinct states to precisely describe the volume and dynamic range of just that single snapshot. Section 3, Calculating Bitrate Capacity. Now that we have the frequency, or our sample rate, and the precision, our bit depth, of our snapshots, we really need to calculate the sheer volume of that resulting information flowing through our cables over time. The formula for this is super straightforward, but it's incredibly important for system design. Multiplying the sample rate by the bit depth gives us the bit rate, which is measured in bits per second.
To put that into perspective, a simple MP3 audio file requires just a tiny data pipe, hovering around 128 kilobits per second. But an uncompressed 4K video stream, that demands a massive 22.3 gigabits per second pipe. Understanding this fundamental math is exactly how we prevent those dreaded network bottlenecks.
And that brings us to an absolutely critical piece of advice for your test. You must always, always differentiate between a lowercase b, which stands for bits and is used for network transfer speeds, and an uppercase b, which stands for bytes, used for hard drive file sizes. The golden rule here? A single byte contains a block of exactly 8 individual bits. Confusing these two letters is a classic exam trap that catches so many people. If a question asks about network capacity and you mix up your bits and bytes, your calculations will be thrown off by a massive factor of 8. For example, an 8 megabyte per second file transfer requires a 64 megabit per second network connection. So please, always double-check your capitalization when reading test questions and spec sheets. Section 4. Codecs and data compression. So, in the real world, trying to push 22 gigabits of raw 4K video over standard physical networks will instantly crash our systems. Let's see how we actually manage that much data. To avoid completely maxing out our bandwidth, we utilize codecs. The word codec is just a clever little mashup of coder and decoder. These are software algorithms, or sometimes hardware chips, that mathematically analyze the digital signal, encode it to shrink it down to a manageable size for transport, and then decode it on the display end. Compression algorithms are wild. They can take an overwhelming 1.5 gigabit per second uncompressed 1080p video frame, squeeze it through a codec, and shrink it down to just 5 megabits per second. Once compressed, it gets packaged into a specific file container, like an MP4 or an AVI, for seamless streaming across the internet. It basically works by finding repeated data patterns and saying, hey, I don't need to send the exact same blue pixel 5,000 times. I'll just send the code that says, make this whole block blue. As an AV professional, you absolutely must understand the two fundamental ways codecs compress this data: lossless and lossy. Lossless compression provides a perfect, 100% accurate mathematical reconstruction of the original file. We use this for critical data where you literally can't lose a single digit, like spreadsheets or text documents. But the compression ratio is pretty low. Lossy compression, on the other hand, intelligently discards unnoticeable audio-visual detail, data our human eyes and ears can't even perceive anyway. This allows for extremely high compression ratios, making formats like MP3s and H.264 video absolutely perfect for streaming media. Section 5. System noise and degradation. This brings us to arguably the most important concept in this entire explainer, the ultimate reason the modern AV industry relies so heavily on digital formats in the physical world. In the physical world, every single cable, connector, and amplifier introduces a small amount of electronic noise to a signal. It's just unavoidable. Because analog signals are continuous flowing waves, the receiving equipment mathematically cannot distinguish between the pure original signal and the newly added noise. This means every single generation of copies, or every time you boost the signal over a long distance, you are continually amplifying that noise until the original signal is permanently degraded and, frankly, practically destroyed. Digital systems, however, they fix this problem entirely. Because they just read discrete, rigid numbers, ones and zeros, they are highly resistant to noise. Even if a digital signal gets physically messy and degraded over a long cable run, a digital repeater can look at it and say, well, that wavy bump is closer to a 1 than a 0. It simply ignores all that analog path noise and instantly snaps the messy signal back into mathematically perfect, identical binary square waves. Every digital copy is a perfect, flawless clone. It's brilliant. Section 6. The Master Exam Synthesis. Okay, we've covered the complex physics, the underlying math of sampling and bit rates, and the mechanics of signal flow and compression. Let's lock this knowledge in for good. This master synthesis matrix is an incredible study guide. It perfectly contrasts the two worlds. On one side, we have the continuous, variable, noise-amplifying nature of the analog dimmer switch, which is measured in direct voltage, and on the other, the discrete, perfectly reproducible, noise-rejecting precision of the digital fan controller measured in sample rates and bit depths. Truly understanding the exact differences on this chart is going to go a long way in ensuring your success on these exam topics. So, as you wrap up this explainer and continue grinding away at preparing for your certification, I want to leave you with a final thought. Now that you understand the fundamental math and physics behind how we capture and digitize reality, how are you going to apply these rules? The next time you're speccing out a network switch or troubleshooting a really noisy audio line, remember the Nyquist theorem, remember your bits versus bytes, and use this foundation to architect the flawless, high-fidelity systems of the future. Thank you so much for joining me to explore the signals that power our world, and I'll catch you in the next explainer.